Hello everyone, this is our project, Fully Convolutional Network with Age Labels for Semantic Segmentation. In this part, I will introduce you about some basic background. The first part is segmentation. We all know that we can classify an image into a label. This is classification. And we can classify objects in an image and bound them by bounding boxes. This is detection. And we can classify and label the pixels in an image. This is segmentation. Here is an example about classification. We can classify this image into these labels and with probabilities. And this is detection by using facial detectors. And this is segmentation. We label and classify each pixels. And this is fully convolutional network. In convolutional neural network, we use downsampling to capture semantic information, and we use fully connected layers to predict our picture into a label. And because of the dense layers, the input size is fixed, and we lose away spatial coordinates by using downsampling. And in FCN, all layers are convolutional layers, and we use upsampling to recover spatial information. And because there is no dense layers, the input size can be any size, and the output is pixel-wise prediction. This is a CNN. We can see the input is a fixed size picture and the output is a label. This is FCN. We can see the input can be any size and the output is a pixel-wise mapping. As for upsampling, a general way to do is use bilinear interpolation. And these 4 red points are the input and the green one can be calculated by this 4. And because we use downsampling to capture the deep features, and the downsampling it can lose lots of spatial location. So we can add skips to deal with this problem. Here is the example. We can upsample this pool 5 with stride 32 to get this FCN32s. And we can see the performance is really bad. And here we can also upsample this pool 5 with stride 2 and combine it with pool 4. And then add them and upsample with stride 16s, we can get FCN 16s. And similarly, we can get these FCN 8s. And we can see when we add more shallow layers, we can get a better performance. In this part, I will introduce you about address convolution. We can modify this read R. And when R equal 1 is the standard convolution and 1 is greater than 1, this is address convolution. Here is 1D example. In this case, the rate is 2, and we pad 2 zeros in each side, and we also insert 1 0. We can see the output is 5, and in standard convolution, the output is 3. And here is the 2D case. And we can see when we change the read, we can enlarge the feature map. And also consider the parameter of filters, because we should only consider non-zero values, so the parameter of the filters stay constant. And here is the example of address convolution. The first row is standard convolution. We use downsampling stride 2, and then we filter this image by this kernel. And then we do upsampling with stride 2, and we can see the loss of spatial information. And here, we do the address convolution with this filter with the same kernel size. And we can see a better performance by using the address convolution.
Our project is inspired by the boundaries provided by the scale dataset. However, in traditional fully convolutional neural network, These boundaries are not used when computing a loss, which means no matter what the label is predicted on the boundary pixels, they will just be ignored. In that case, we decide to add some new losses according to these boundaries. It would be relatively easy to derive the boundary of the segmented ground truth, and we set the pixel at 1, otherwise 0. The boundary of the ground truth is shown in the left image. The right image shows the boundary derived from this prediction map. To derive the boundary of the segmented prediction, our definition is based on the 4 connected neighbors and 8 connected neighbors. If they are all same label as the center pixel, we set this as non-boundary, which means 0. To compute the loss, we first doing image inverse on the ground truth boundaries, which provides the effect of the minus as the general loss function definition. Then we compute the pixel-wise product between the inverse ground truth boundary and the predicted boundaries. Wrong prediction would be penalized as 1 and otherwise 0, which is shown in above figure. Our final loss is computed by sum up all the white pixels and then normalize it by the number of the ground truth boundary pixels. To test our network, we trained the traditional network and the new network with the edge losses for the same amount of epochs. Here are some results from the Pascal dataset. Here, the human leg, our network provides a better result. Clothes of the human, the hands, the legs, they all provide a better result. However, when an object includes some texture of another totally different object, the network tends to fail. But for the other cases, which is simple like this airplane, the car, where the background is clear and our network tends to provide better result. Lots of results like the human hands, the original network do not provide such detail, and our network provides these details. Both networks tend to fail when counter the cases like this. Here, the tree leaves have lots of tiny boundaries. Both networks cannot work well, and here the same cases like the chair, they can do well prediction on the humans. But for the chair, it tends to be a failure. Another case is that both networks tend to fail is that when counter the image like this duck, it have lots of texture that mimics the background. In that case, both networks tend to fail. We also made some real-world tests based on the photography taken by ourselves. Here, this is the image we taken. The prediction of the original fully convolutional neural network and the network with the edge losses, we can see that our network tends to provide better results, especially when lots of objects are bonded together, and the human for much slightly better. But it's also a failure when encounter the trees with lots of leaves and they cannot provide dedicated results. The pigeon, this is a good cases to show that the original network tend to connect both pigeons together while our network can separate them well. The airplanes, they all shows that when adding an edge losses, they can be a nice result. We also made some fancy tests on the observation we found. We used the image of 2 bottles, and this is the original image, the segmented result of original SCN and the network with edge losses. And then we show the same image on the computer screen. They can't distinguish whether the object is an image on the computer screen or it's a real bottle placed in front of the screen. As a conclusion, our networks with the edge losses can provide better results, especially on the image boundaries.